Thank you, Jerry. I have to confess to being both a modeler and an economist, so put up with me. Also, I'm going to talk about linking economics and hydrologic models. I'm going to use a very narrow but I think pertinent case, which is the future and I think perhaps the biggest shift in California water policy, the SGMA Groundwater Management Act. And Jay will disapprove because I don't have any insights, but I do have numbers. On the other hand, Gary would appreciate it because he says, answer the question. And Peter told us that we have to have co-equal goals. So this is the money goal and the water supply one. And this is done jointly with my colleagues, Duncan McEwen and then Steve Hatchett later. Estuarine systems, by definition of the interface between freshwater and saltwater, at least according to my thinking, and therefore the freshwater flows determine, and the rate of those flows determine the state of the estuary, and the freshwater flows are influenced by human use of water. This is driven by economic and environmental goals. We are the big predator. And it's subject, of course, to geologic and hydrologic constraints. And so omitting either of these components for policy results in errors. And you get feedbacks in both directions. For instance, with groundwater, which I'm going to talk about, because it's part of our California water supply, a critical part, you get overpumping in the lack of bad economic criteria, which is what we have currently. On the other hand, as we'll see, that if you regulate that, that will change both the quantity and the value of water available in different parts of California. And this will affect the estuarine flows, particularly through the delta. I want to go to a point that Will brought up earlier on, and that's a point of scale, because an integrating model is really scaled, and it really hits things very toughly when it comes to trying to put economics in, because particularly agricultural economics, you tend to grow one, at the most, 2 crops a year, and so you're very lucky if you've got monthly demands for water. And yet, we're trying to interface these with hydrologic or groundwater models that run perhaps on a daily basis or weekly. And so we have to, or maybe even hourly in my slides, we have to aggregate up very coarsely, and you can see the wince going across the face of my hydrologic colleagues when you say, come on, throw all these daily observations together and give me a monthly mean. You know. On the other hand, spatial resolution is also a problem. That hydrology, of course, we have our nodes, and yet in economics, we often ignore spatial resolution, which is a really bad idea when we're getting economic results from physical inputs. So we have to be aware that these aggregation, disaggregation errors are nonlinear, and of course the aggregation errors are much easier to aggregate than disaggregate, since disaggregation requires additional information. And in this particular example, we're aggregating the groundwater models to a monthly basis, and we're disaggregating the economic agricultural models also to a monthly basis based on crop water requirements. Likewise, we're taking aggregate hydrologic results, and these current ones I'm going to show you in a minute are not based on groundwater basins. They're based on what we call agronomic units, which are institutional units, and there's 27 of them in the Central Valley. But they do overlie, to a greater or lesser extent, groundwater basins. And so we have to try and have these models talk to each other through a process of aggregation and disaggregation, since the feedback go in both directions. So what's happening in California? This year, we had a really remarkable thing happen. We caught up with the rest of the world and the rest of the country we're high-tech here, by putting forth some groundwater management legislation. Up until then, and as we speak right now, our groundwater is, with a few rare exceptional examples, completely unmanaged, and people pump whatever they want to pump. I know this, I have my own wells, and I pump what I want. And by the way, my well information is secret. You can't have it. Why? I have no idea. I had to file it with the county, and they're not allowed to tell you what's going on. With the comparison with Rob's Australian data set, it was just extraordinary. And I was reminded the other day how well the Australians have run the drought. I'm a little bit biased there. But compared with California, which is currently running its drought through two things. One is groundwater, and one is water markets. And guess what? There's no information on either. We don't know what's going on with groundwater, and we don't know what's going on with water markets. It's truly amazing. Okay, moving on. Let's look at this thing of sigma. I'm writing a paper with a couple of colleagues, Duncan McEwen and Steve Hatchett. And fundamentally, we are trying to find out, answer the question, as Gary would tell us we have to do, is what is going to be the impact and the cost of this Sustainable Groundwater Management Act, which in theory doesn't come in till 2042, but in fact I hope will come in significantly before that. And so we're linking two groundwater models with an economic model. And we have spatial aggregation to these production regions. And we have time aggregation, and we're consolidating daily simulations into monthly growing season units. Now, we are taking the worst possible case for sigma, and these are the basins in California and the CASGEM, and these are listed as high, medium, low, or very low priority. And it's quite clear to see, I'll see if I can press the right button on this pointer, that these ones here in the Central Valley are the ones where we are most at risk. So these are the high basins. We have a few down here in Southern California. What we're going to do with these, basins is, first of all, we took the hydrologic models, aggregated them, looked at the balance. We said, let's take the worst possible case for the valley. No new water supplies and surface water. The worst possible case. How do you bring a basin into balance if you've got overdraft? You have to reduce evapotranspiration. No ifs, buts, or ands. It's a very simple equation. And so you have to take agricultural irrigated land out of production. That's it. How much will have to come, and how much will it cost? Here's a set of 27 regions in the valley, and but I've given them the general. These are Sacramento Valley regions. This is the Delta, and this is San Joaquin Valley, and these are Tulare Basin. Now, this is the percentage of the groundwater pumping that took place between 2000 and 2009 in each of these regions that can continue if the basin is in steady state over a 10-year average interval with 2000 to 2009 pumping rates. So for instance, this basin in the central Sacramento Valley can get by with about an 8% cut in groundwater. This basin in the upper end of the San Joaquin Valley has to take a 60% cut. This basin in the Tulare has to take a 90% cut in their groundwater. And so this is the first time this data has come out that I'm aware, because nobody has wanted to grasp the tough problem. How much are you going to cut, who's cutting, and where? And here it is. It could be wrong. It's very aggregate. It's based on 2000 to 2009, but it is based on both the DWR C2V SIM model and the CVH model from the USGS. So, and in a nutshell, we see that about 45% of the basins have to cut 10 to 15%. Another 45% have to cut about 40%. And there's 3 or 4 basins, and we can see them right here, and I've deliberately taken the names off because I don't want to scare people, where they're going to have to make really incredibly stringent cuts in their groundwater use to reach a steady state without additional surface supplies. This is the driver. Put this into the economic model and we get the money. So this is answering the question, well, okay, what's it going to do to water values? In the upper Sacramento Valley, no change. As we get down into this area here in the lower Sacramento Valley, water values, the imputed value of water is going to jump from in the $50 to $70 range, and it's going to double. The delta is relatively unaffected, no change in the delta values. As we move into San Joaquin, we start to see these enormous increases in value. And so this region here, which has been managing its water on a $100 an acre foot basis, is going to be facing $380 to $400. This is 2030 levels of development, by the way. As we get to the Tulare Basin, we see a really remarkable increase in value. What's this going to do with the delta? This means that the money gradient across the delta in water value, which is somewhere in the region of about $400 at the minute, is going to jump to about $500 to $600. That the gradient of pressure to move water across the delta is going to increase. The opportunity cost of water below the delta is going to increase. And so this concept should have really significant effects on both infrastructure, delta management, and where do we invest. But the economics is interesting because if you look at the groundwater cuts, and the green is Tulare and the blue is San Joaquin, we see similar average, about 28% cut in groundwater. But you only see a significant acreage cut in the Tulare Basin, about 8%. And then the revenues, because the farmers are adjusting on all these ways and they're taking out the high water using low water value crops, and they're changing their technologies. The actual economic burden looks manageable. Certainly in the Sacramento and San Joaquin, not a problem. In Tulare, we've got to eat several $100 million. But I would emphasize that our initial analysis, which I'm not showing, shows that in the long run, you'll have about a 15-year loss of revenue. And then after that, your positive revenue for the infinite future with a stable, long-term sustainable basin that allows you to develop high-value crops. Here's some details here that we're losing about 1.3 million acre feet per year average groundwater pumping to stabilize these basins. We are going to lose about 330,000 acres per year of evapotranspiration. Does that mean we're going to have vast dust bowls? No. What we're going to do is we're going to have a shift back towards the greater use of fallowing as an agronomic rotation and weed control and salinity control and nitrogen control. There will be some positive effects as well as negative effects. And it'll cost us somewhere in the region of $320 million in terms of lost revenue. We will save several $100 million of pumping costs and well replacement capacity costs. So in a nutshell, the take-home message, as I see it, is that estuarine and water supply policies are intertwined, and anyone who's been working the Delta will know that. We assume that sigma can stabilize groundwater, has to stabilize by 2030, not 2042. The costs of this vary tremendously throughout the valley, And the increasing water value will make the north-south differences in terms of both water and economic gradients greater. And this means that integrated water management decisions will need to be reconsidered under sigma, because the scarcity and the availability of water is going to change quite substantially. Thank you.